Hey guys, this video is about half-life calculations. The application that's used most often is with radioactivity. Since radioactive decay is a first-order reaction, a half-life, before we get started, is, let's say you had 100 molecules of a radioactive substance. The half-life is the time it would take for 100 of those molecules to degrade into their product and for you to have 50 of those molecules remaining. If it takes 10 years for that to happen, your half-life is 10 years. The symbol for half-life is T1/2. You could also use molarity concentrations. If you were using molarity, how long would it take for that 2 molar solution, or that 2 molar of anything, gas for example, degraded till when you had 1 molar? The T1/2 for that is whatever you experimentally determine it to be, right? So it's the time it takes for half of your original sample to decompose, to disappear, to get converted to products. And like I said before, the most salient example of this is radioactive decay. There's a special way of deriving the half-life expression. You can either memorize it, or you could sort of do what I do, is try and memorize as little as possible and just figure it out, derive it from the integrated rate law. Now, because radioactive decay is a first-order reaction, we use the integrated rate law that you've already memorized, right? This is the first-order integrated rate law. Radioactive decay is first order. We expand this expression, and well, what we realize though, actually we don't expand it yet, back up, sorry. We look at this and we say, A0, that's our original amount, our original concentration. And A at times T is half of that, right? So let's take this first example up here. If you take the number 100 and you divide it by 50, what are you going to get? You're going to get the natural log of 2, right? Or if we took the 2 molar divided by 1 molar, you get the natural log of 2. So this ratio, when we're talking about a half-life, is always 2. So this equation simplifies to the natural log of 2 is equal to K times T for first-order radioactive decay. We don't actually have to know concentrations because we're referring to a situation in which that ratio is always 2. So if you're talking about a first-order radioactive decay or just a first-order reaction at all, you can use this equation to solve for the half-life, as long as you know K, the rate constant. You could simplify this even more. The natural log of 2 is 0.0693. So 0.0693 is equal to K times T. And really we should call that T1/2. So T1/2 then is equal to 0.693 over K. Or T1/2 is equal to 0, or I should say the ln of 2 over K for your first order reaction. An example of this might be, let's say, we'll go up just a little bit, cyclopropane. Cyclo meaning, connected in a ring. Cyclopropane, very unstable because it's kind of hard to bend these bonds into this direction, right? So there's H, 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 H. Cyclopropane degrades in a first-order reaction with a little bit of heat. If we put an arrow and a triangle, the triangle means with added heat, it will degrade into CH3, CH, and CH2. Now if we know that the rate constant for this reaction, K, is equal to 9.2 seconds to the minus 1, we could easily answer the question of what's the half-life. T1/2 is equal to the ln of 2 over our value of k, and that's equal to 0.693 over our rate constant of 9.2 seconds to the minus 1, giving us 0.075 seconds. So as long as you have the rate constant, you can easily determine the half-life. So what this means is it takes 0.075 seconds for this given sample, however much you have, to degrade, for half of it to degrade. And that is how you apply an integrated rate law that is first order for half-life.